Nobody's yet. Wisconsin yet. Nobody's yet at the cookies. Like that. It's a great pleasure to welcome today's speaker, Dr. Clare Huang from the University of Chicago. And this is the beginning of yet another season of our Colloquium series, which is one of the, for those of you who are new in the department, whether graduate students or otherwise, this is of course a highlight of our week, is to have outside speakers and scholars from the building come in and talking about what they've currently been working on. And to start with Clare is a real blessing for us, I think. And so thank you for coming from Chicago and for being willing to lead us on. And I'll say, just before I continue with Clare's introduction, don't forget also about the Wednesday department seminar, which is at 2:30 in the same room. That's another really highlight that you want to make part of your schedule to the extent that you can. Clare is a native of Hong Kong, where she spent the first 21 years of her life and earned her BS in physics from the Chinese University of Hong Kong. And she double majored in mathematics and German languages. That's a combination. Probably calculus by Leibniz in that double major, but I don't know about that. Upon receiving those degrees, Clare traveled to the U.S. to study at the University of Chicago under Professor Noboru Nakamura and developed the finite amplitude local wave activity theory, which we'll hear a little bit about today, I think. And that's opened up, really it has. We had a nice conversation today, and I was eager all summer to have Clare come, because I've stumbled into these issues about why is the jet wavy and how do you measure it and all that. And they've been doing this in Chicago for 5 years in a much more sophisticated way. So this study has opened up all kinds of new interpretations about extreme weather and the environments from which extreme weather events emerge. So as I say, I was really eager to have Clare come and visit, and she was very happy to do it. So since graduating in the spring of 2017, she's been working for as a data scientist at a company called Conversant, where she builds machine learning models of language for a variety of clients. That's about as much as I can say about it, and maybe that's partly accurate, I'm not sure. That no more can be disclosed. And in addition to these professional accomplishments, I told Clare I would tell her this, because on her page, bio page, she has a link to a YouTube page. She's a fantastic pianist, and she writes and composes music as well. And I'm telling you, it's really worth going and checking it out. Today, Clare is going to tell us about her recent work on blocking, bearing a provocative title, the same one as her recent paper in Science, Atmospheric Blocking is the Traffic Jam in the Jet Stream. So Clare, thank you again for coming, and we're really looking forward to your presentation.
Thanks, John, for the introduction. And I'm really happy to be here and talk about the research work that I have been doing. And this colloquium will focus on the use of local finite amplitude wave activity to study atmospheric blocking and the insights we gain from analysis that blocking can be seen as a traffic jam in the jet stream. Okay, so here's the outline of my talk. So first of all, I'll review what atmospheric blocking is and why studying it is challenging. And the second part will focus on introducing the finite amplitude local wave activity theory, which serves as a theoretical approach to study blocking. From the theoretical framework, we realize that there is a threshold behavior of a local wave activity that is analogous to traffic jam, such that we can actually reduce this nonlinear phenomena into 1D simple time model. And last of all, I will talk about some exciting work from our group that follow up this traffic flow model work and the potential application for it to explain why blocking projection from model ensembles have a low confidence in a warming climate. So first of all, as an introduction, so on the right-hand side, I'm showing the globe with the wind field at 250 hectopascal, which is around the pressure level of the tropopause. You can see there are two red bands over the northern hemisphere and also southern hemisphere mid-latitude. That is the jet stream, the fastest corridor of air that is traveling, that's moving eastward. You can also see it in the annual mean of the solar mean wind plot. So it's a plot of pressure versus latitude that the core of the jet is at this level. the weather system like cyclones and anticyclones are migrating along the jet streams, but sometimes it can be blocked. Like for example here, like there is an anticyclone that is stuck here and like not going forward. So sometimes the weather system is blocked and we call that blocking. So blocking can lead to some severe extreme weather conditions at the surface. Like for example, the Russia heat wave in 2010 is associated with a stagnant anticyclone over Russia. Here is a plot of average surface temperature and the geopotential height at 500 hectopascal, and we can over 11 days. So we can see that like this is a persistent pattern, and that leads to casualties in locally. Not only heat waves, but blocking can also be related to drought. Like for example, in the 2013 to 14 winter, there is a persistent ridge that stays at the East Pacific, and it is named the Triple R. And then I checked what is that about. It's called the ridiculously resilient ridge. So some people gave it a name, and you can see the precipitation of that year is particularly low. And so the reason is that the ridge actually steers away the storm such that it doesn't reach this part of California. So on top of the omega block that we have seen for the Russia heat wave, and also the dipole block that we've seen on the last slide, there are also different kinds of blocking geometry, like for example, anticyclonic wave breaking or the cyclonic wave breaking. So it also involves like a disruption of the jet streams, and for that two cases, it involves the extreme transport of moisture across latitude. And so you can see there is a difficulty in defining what a block is, given there are like so many kinds of blocks. But like a general consensus is that like the jet stream is disrupted, and there is like an anomaly that's stay stagnant at a place for quite some time, like maybe beyond 5 days or 4 days. It is still a debate. Okay, and I'm showing some graphs from the review paper on blocking by Tim Willings, and here are 3 examples of blocking indices based on the zonal anomaly, that absolute field reversal, and also one indices focus on the combination of the two. So usually the blocking indices are defined this way, and it depends on like what kind of field you are looking at. Now they're looking at the 500 hectopascal geopotential height. Sometimes people look at the potential temperature on a PP surface. The top panel shows the climatology of blocking frequency they compute using these indices over multilinear analysis data. And the dots here suggest like whether there is a significant trend of increasing or decreasing throughout the period. We can see that for the climatology, the peak more or less agree with each other among different blocking indices. Like there are over the Pacific and over the Atlantic, but the precise location of the blocking pattern are slightly different. So when it comes to studying climate model response, it poses a problem. Like so in the lower panel, it shows the northern winter blocking projection from multi-model mean RCP 8.5 model ensemble, and the color is indicating the trend of blocking over the region. So you can see that they actually differ quite a lot. when using different indices to pick up the blocking events. And since the indices don't agree with each other, like there is low confidence of like telling whether blocking frequency would increase or decrease in a certain region. So on top of the discrepancies in the blocking indices, there is also something about the model. That is, it seems unable to estimate the blocking frequency correctly. Here, I'm showing the plot of results from the same blocking frequency of blocking distribution over different longitudes. And the dotted line is from area interim, so we may regard it as like the answer to check or the true results, while the other lines are different model ensembles. So they tend to underestimate the blocking frequency over the Atlantic, while over the Pacific, like some model has been doing fine, while some are still underestimating it. So overall, blocking is underestimated by the model. In Tim Wang's research paper, review paper, he mentioned there are like two difficulties in moving forward when we study blocking. The first would be the limitation of the model, and the second one would be the lack of theoretical ground to understand the mechanism of blocking. So when we go to the theoretical tools that we have, when we look at the wave mean flow theory, like is the current formula sum sufficient to study blocking? There are different quantities, for example, like eddy kinetic energy or like wave activity. And wave activity is a natural measure of blocking because this quantity captures the amplitude of wave. There are some wave activity flux formulation, like by Hoskins, Plum, and also Takaya and Nakamura, that focus on like the formulation of the wave activity flux factor or the EP flux factor in this wave activity equation. And also there are some studies of block based on this, based on the EP flux. However, in all these formulas, there is actually a small amplitude assumption of wave when they are deriving this equation. So so the wave activity definition is this one, like the PV anomaly square divided by the meridional gradient of PV. But then this term is actually never computed when people are looking at the EP flux factors. So they only look at like how the wave propagates, but then did they really see like where the waves are and like how large is it? This term is never computed, and that one is very often just used as a diagnostic tool. So in order to make this wave activity useful for finite amplitude wave problems such as blocking, then there is a need to like generalize this to finite amplitude regime. And this is what I have been focusing on for my thesis work. Which is to generalize the wave activity to like finite amplitude regime such that it is well behaved for large amplitude wave. So this is actually a work that follow up my supervisor Nakamura's work on the finite amplitude local wave activity, which is like a Sono mean formula sum to a local extent. This wave activity, I will call it LWA in the following slides, is a measure of the meridional displacement of PV from its zonal symmetry. The way to compute this may be a bit technical, but then we're looking at the area bounded by a contour and the equivalent latitude which encloses the same area as the contour, and see how far it deviates from this line, and we do an integral of this PV anomaly, and it would always be a positive number given the definition. Like we sum up the contribution from above and below. And it may be a bit abstract to just look at the definition. So maybe I can show an example where I compute the wave activity from the quasi-geostrophic potential vorticity at the trouble pulse level. This is a day where the Hurricane Sandy is still inshore, and it is actually somewhere around here when the block grows. It kind of like Sandy goes with it inshore to New Jersey that day. And you can see, so the QGPV field is rather noisy, but when the wave activity is computed, like the block is highlighted. I can show you a movie such that you can see the behavior of wave activity.
Excuse me. Question.
Yes.
So when you do that calculation for the wave activity, the sort of classic formulations, 1/2 q prime squared over q bar y. The way that that's phrased, it looks like you're doing an integral of the deviation of the PV from its reference latitude, or some reference latitude.
Yes.
How do those link together? Maybe I'm missing something obvious.
Well, here in the definition. So here is so it is the anomaly somewhere from like from the equivalent latitude to there. In fact, in the small amplitude case, it will converge to the form of the linear wave activity, like with the gradient. But then, like for the finite amplitude case, it is still well defined positive. And, yeah, I have actually done some work to show that, but I don't have it.
Okay.
Oh, right. You can check out the paper from Solomon and Nakamura 2012 in JFM. They have shown the like for the Solomon version how this will converge to the linear version when it's in small amplitude. Yes.
I guess you could kind of go back and forth between the two if Q prime goes like minus eta dq bar dy. But I was just thinking, in the quasi-dystrophic version that you have, aren't there limitations when the Q bar y is 0 or negative? And that your new method would avoid that problem. Is that true?
Yes, my method. So I am not using Q bar as the reference date, but I'm using Q ref or the equivalent latitude as the reference date. So the way I compute the equivalent latitude is to look at the global distribution and then try to rearrange a PV from low latitude to high latitude in a monotonic manner, so that my reference date is always monotonically increasing. And the way to define the reference state that way is that it will be invariant unless there is non-conservative process like irreversible mixing that homogenize the PV. Then the reference state that I'm calculating will change. Like the slope of it will change. To show a movie. Yes, here it is. Okay, so here I want to show a movie of how the wave activity looks like when I'm computing it over a few days. So you can see that it is continuous and it evolves with how the wave propagates. So we can see right there is another block there over. Because Yeah, and the plot I was showing on the slide was from here, where there is well, it just lasts for 4 days actually. So maybe in the blocking community, some people would not regard it as a block. Okay. And so on top of being able to capture the magnitude and the location, this local wave activity also have a very good property that it anti-correlates with the zonal wind. So we will know the reason after we look at its evolution equation. Here I'm showing a column average over the 60-degree sector where the plot I showed you on the previous slide sits at. And the blue line is the local wave activity, and the red line is the zonal wind being column average over a domain. We can see that over the days where the blocking occur, there is a robust anti-correlation between these two quantities. So because of this, we think that local wave activity would be a good proxy for like measuring blocking, because block itself means like the wave slows down or stays there. So if there is a large local wave activity, it already directly implies that the zonal wind is decreasing. So it seems to be a good index that captures the characteristics of blocking. But then it is not just an index, it is a quantity that is derived directly from the Kelvin circulation theorem. The good thing is that we can write out the equation and include the nonlinear terms that was not present in the linear wave mean flow theory. And if we are looking at like a column budget, instead of like layer by layer, the equation is rather simple. The local wave activity tendency would be given by different terms, like the zonal wave activity flux convergence, which mainly are the wave from upstream. And the second one is the meridional eddy momentum flux divergence. So note that in the equation of the zonal wind, this term is also present, but of opposite sign, and therefore they have the robust anti-correlation relationship. The third term will be the low-level eddy meridional heat flux, which is the heat source from below. And given that we are writing all the conservative process in this like in the manner without small wave assumption, we can safely interpret the residual as the contribution from non-conservative forces altogether, plus maybe analysis error or the QG assumption error to the last term. So we can use this equation to do some diagnostics without worrying the higher order terms being thrown away. So how do we compute the contribution of different terms to the synoptic variability of Rossby waves? In my paper in 2007 in GRL, I'm computing the co-spectral between zonal wave activity tendency in different terms. So you can imagine the wave activity tendency will be rather noisy after you do the time derivative. So this is a way to do the statistics for the eddies. Here I'm showing in the Pacific and the Atlantic sector how the co-spectra looks like. Well, our main takeaway is that the major contribution in the synoptic time scale would be from the zonal wave activity flux convergence and also the residual. The low-level eddy meridional heat flux would contribute to the low frequency variability of those waves, and their contribution is rather insignificant in the synoptic scale. So that's the takeaway. Given this observation, when we think of studying blocking, we may focus on mainly the zonal wave activity flux convergence, since it is a dominant term of this wave activity budget in that time scale. Okay, so then we would like to find some blocking events to study. Here I'm showing the covariance of the wave activity and the zonal wind in northern winter from area interrim. So we can see there are two negative peaks over the Pacific and the Atlantic jet exit, where the blocking events happen most of the time. The figure below shows the scatter plot of the zonal wind, column average zonal wind versus the wave activity over the 2 points of at the peak for Pacific and the Atlantic. So you can see they are more or less falling on the same, on a straight line with a slope of like 0.5. So there is an empirical relation between the zonal wind and the wave activity. That depends on the location that we are looking at. Like and for blocking, you can, so what would happen when blocking occurs? So the wave will slow down and the wave will grow to a large packet. So we can, so we pick the events at the lower right quadrant which fulfills these criteria to study. By the way, these two plots are 4-day average wave activity and zonal wind. So,
Claire, is there any significance to the fact that point B is in the left exit region of the mean jet, and point A is in the right exit region of the mean jet in the Atlantic? So in other words, I immediately see that and I see A is being forced, the air is being forced to sink over point A, and it's not being forced to sink over point B by the climatology. And I wonder if that doesn't drive the Atlantic basin a little more crazy in terms of how does blocking actually set up. And the mode that varies primarily in the Atlantic, as I understand it, is the meridional shift of that exit region, and it's just the opposite in the Pacific, that it's extended or retracted as the primary mode of variability of the climatological jet. So there's differences in the orientation of the jet in the Atlantic basin might underlie all of the differences in the blocking. Is that what you're finding?
We haven't looked at that, but I suspect like the orientation of the jet really matters in this analysis. Like given that we always zonalize our means, like zonalize and mean state like according to latitude, but then the Atlantic jet is like inclined. So it's like even like if things are following the jet, there is a non-zero wave activity over there. Yeah, this is something that I have to think about or look into.
How did you, it looks like in the Pacific Basin, you used a negative zonal wind, but in the Atlantic Basin, it's a stronger, it's more strongly negative. What was your selection criteria for the, or are those the red colors just identified blocking events?
So I think we are picking like 24 events for each.
Okay.
Yeah.
So those are identified blocking events.
Yeah, but then like we like it guarantees that like at the end, like where the zonal wind is reversing, and for a large amplitude, it would definitely be the case of blocking. So maybe it is pretty. Like it may not be like a very robust definition to pick up blocking, but then like we know that definitely these events are blocking. So we look into like the composite of it. So here I'm showing the composite of like the 24 events of that we take over the Atlantic. And there are, so here shows the wave activity, the zonal wind, and the zonal local wave activity flux. So we see that in the Atlantic, there is a burst of the wave activity flux and preceding the burst of wave activity. So how to understand this observation? In the local wave activity equation, the zonal wave activity flux term, there are actually three terms. Like the first term is proportional to wave activity with the effective velocity uref. Uref is the reference state backed out from the PV reference state with some by inverting an elliptical equation, and that uref is a hypothetical zonal wind state that if there are no eddies or all the eddies are removed from the current snapshot, what will the zonal wind be? So that is the interpretation of this reference state U. So if no non-conservative forces are dissipating the zonal wind, then it will remain the same. Okay, and the third term is proportional also to the wave activity, but then there is a second term in here that is proportional to wave activity square and is negative. So this term has never been captured in the linear wave activity flux formula. It will be regarded as higher order term and thrown away. But then this term seems to be important when we are looking at blocking. As the wave grows, this term will be large and cancel out the two terms. So this is what we observe in data. In the yellow dots are the sum of the linear terms, while the total sum of it are indicated by the blue dots. So it is not clear here how they are distributed. So if we look at the box plot instead, we find that at least the median seems to fall on a parabola. And there is a maximum of wave activity flux that if the wave activity exceeds certain point, the flux will go down. So this is observed both over the Pacific and the Atlantic. So given this diagram, what would you think is any physical system that has this property? But my talk's title already have spoiled the answer. That would be like the traffic flow on a highway. So why would I say that? So you can imagine when there are not many vehicles on the highway, the number of cars passing through a point would increase when there are more cars getting on the highway, but then it will reach a point where it saturates the highway's capacity such that the driver has to slow down, so that the overall flow or the traffic flux would decrease when there are more and more vehicles getting on the highway. Like in this regime, it will be like here. So given that analogy, we attempt to formulate blocking as like traffic flow, traffic congestion of Rossby waves. So we are building a 1D model to capture this behavior. So given these three terms, we formulate the traffic flow model with a flux term that has a term linear to the wave activity density and a negative term that is proportional to the square of it. The alpha here is the interaction between the zonal wind and the wave activity, which is the empirical constant I said that when fitting a straight line on the plot of U and A. At the same time, there are also some other terms in this model to make things more realistic. One is stochastic forcing term, which represents the transient wave forcing. Another would be a drag term or linear damping term, which represents the mixing. The last term would be a numerical diffusion term, such that to maintain numerical stability if we are integrating this equation. The wave activity is partitioned into the stationary wave and the transient wave component. So here the A hat is a transient wave component, and the stationary wave component is included in the term C, which is the group velocity term, consists of like the background flow, the group velocity, and also the stationary wave component. Okay, so we have this model, and then like after choosing some parameters, like here is a case that we have got, like running this 1D traffic flow model. So we can see that the essence of blocking is more or less captured, although there are also some discrepancies. So you can see like after the solar wave activity flux accumulates, it then follows the growth of a block. But then there are also some unrealistic aspects of this 1D traffic flow model. Like first of all, here we have chosen a set of parameters such that the solar wind never reverse. But indeed, if you further vary the form of forcing, it is possible to get a negative failure, but I'm not showing it here. And there is also some approximation, like there is no representation of like temperature or precipitation anomaly. It's just a Rossby wave. And lastly, you may see that like the flux here and the peak of reactivity here is like closer to that in the above panel, because in reality there are likely the meridional transport of the wave activity. So, but we didn't have this in the model. So this is something that we can play with, since this model is so simple. So we are pushing, we are promoting the notion that like it can be modeled as a traffic jam. So what is the implication? That the implication is that the atmosphere actually has a finite width, so that the Rossby wave may get into congestion. So it is not like the wave can travel freely. Like there is indeed a finite width that when the wave activity attains these values, like learn from this term, like the solar wave activity flux would attain a maximum. And that would be the traffic jam of Rossby wave in the jet stream. So in order to study this equation better, we define a saturation level, which is the flux term over like the maximum value it can attain. And then we can see if this saturation level is being approached, then we are closer to the onset of blocking. What affects the proximity to such saturation? So there are three factors. So the first would be the background flow in the jet speed embedded in C. The second one would be the stationary forcing represented in a model by A0. And the third one would be the transient eddy forcing, which directly affects the growth and the decay of the solar wave activity flux. So this, when we are studying how blocking frequency would be affected by a warming climate or like jet shift or some other things, it is not easy to study it with GCM, because like there will be cancellation effect or like coupled effect between different quantities. But if we are playing this in a very simple toy model, we can gain some insight while keeping them keeping the comparison clean. Okay, so here I will talk about a recent study by my supervisor and some other students at U of Toronto, Woodhouse, and also UChicago in the climate statistic workshop Rossby Palooza, organized by my department. So it is a bi-yearly event, and it's a lot of fun. I was in the first organizing committee when this was founded, in 2016. And so they are trying to play with this model and gain some insights of blocking statistics and how it will change in a varying climate. So given the model is cheap to run, they can sweep the parameter space of all the three controlling factors. So here I'm showing an example of their simulation. Here is a Hofmöller diagram. So it is time versus distance that it is traveling, and and here are the total wave activity, the zonal wind, the flux, and also blocking mass. So here they are defining the blocking as an extreme where an extremum of the zonal flux derivative. And I'm showing a simulation that they are using a slower jet, a weaker stationary wave versus a faster jet and a much stronger stationary wave. That the wave is confined in the two bands here. So you can see the change in the blocking mass, the blocking statistics. Here there are more frequent blocking, but they are less persistent. While, yes?
I was just curious, does that relationship with the faster jet, stronger stationary wave explain why the Atlantic is more variable or unpredictable?
So Atlantic is has the stationary wave.
Is the Pacific jet stronger and it's more predictable?
What do you mean by predictable?
You had a higher statistical relationship between wave activity and the zonal flow speed in the Pacific and the Atlantic. And I'm just wondering if it has to do with this relationship you're describing now, that a faster jet implies a stronger stationary.
Oh, I see. Because in the Atlantic, the zonal wind, due to the topography, the zonal wind is not so well correlated with the wave activity. Yeah, that. So that might be the case. So over the Atlantic, I'm thinking, so the stationary wave over the Atlantic, it would affect, but the stationary wave doesn't make it more unpredictable. It's just one of the controlling factors that would influence the behavior of the blocks. But they are indeed different due to the difference in the stationary wave pattern over the ocean. Indeed, here I mostly want to show the effect of a stationary wave, but they indeed have used a faster jet as well. So here is mostly comparing if there is a stronger stationary wave, how would blocking statistics behave? And so in fact, the jet speed and the stationary wave have an opposite effect influencing blocking. here I'm showing 3 blocking statistics measure that they are using: the prevalence, the frequency, and the persistence. And for these 3 metrics, in the parameter space of the jet speed versus stationary wave amplitude, there is a clear transition boundary here that we can observe in all these 3 metrics. That the climate state can transit from a block-free state to a block-dominant state. So this is what we learned from this toy model. And one of the insights gained from it is that, like, at the current state that we are in, blocks are observed frequently, but like they don't last for too long in the real atmosphere, like in this scale. So maybe the present climate is around the transition state, so that when we are running different models, that we are actually falling on like different side of this transition boundary, so that it, like, the model can hardly agree on each other, having a low confidence in like projecting whether like the change in the future climate is positive or negative. Okay, so here's the end of my talk and a brief summary of it. So first of all, I'm introducing the finite amplitude local wave activity as a diagnostic to study atmospheric blocking, because it can capture the evolution of a large amplitude wave and also partitioning the physical processes leading to its progress in different terms. Secondly, the blocking can be modeled as a traffic jam in the Rossby waves. So we only focus on the zonal wave activity flux and can build a toy model that captures the behavior of the block. The third thing is that the capacity of the jet stream, or the proximity to saturation, is affected by, first, the background flow, second, the stationary wave forcing, and the transient wave forcing. And last of all, the parameter sweep with a simple 1D model give a clear transition boundary between block dominance and block free state. The proximity to this boundary might be a reason why model projection has low confidence in blocking statistics. So this is something that has to be further studied and verified. So we are providing some insights from like a simple 1D toy model. Okay, so after the introduction, I would like to introduce like a toolbox that I've been developing to wrap up the code to compute wave activity into a Python package, so that you can compute things in 2 or 3 lines. So there are some Jupyter Notebook examples that you can just stuff in your climate data, and then it will produce the computed results, and then you can plot it out, you can save it. And I'm still maintaining the package, and if there are some new functionalities to add, feel free to raise any suggestions or like issues on GitHub, and I will take care of it. Like, even though like I have to work, I'm still I'm still maintaining this. So yeah. And okay, so that's the end of my presentation. Thank you for your attention.
So this wave activity flux, which what you're saying is it's kind of shut down during blocking because of this traffic jam, right? But the wave activity flux itself is creating the blocking, I would think, that it actually builds the ridge.
Yes.
So it's a natural break on the system as well. Once you build the ridge, you get this traffic jam, and then the wave activity flux would weaken at that?
The wave activity flux would decay to 0 for a while, like when the block is formed.
But
Yeah.
what I'm getting at is there's one assumption built into that, and that's the wave activity flux is created by the movement of the waves. But in reality, in many cases, the wave activity flux is created by an independent entity like tropical weather systems.
Mm-hmm.
And in those cases, you may get continuous forcing of this ridge, which would maintain a traffic jam.
And so you are saying that locally at the block there are creation of wave activity by other systems, or that?
Yeah, what I'm saying is, in many cases, wave activity fluxes come out of the tropics. They come out of a different
Yes.
entity. They're
Yeah,
not.
so
They're
it's
independent.
Yeah, it's from like the meridional. It's so simple. So we are pushing. We are promoting the notion that like it can be modeled as a traffic jam. So what is the implication? That the implication is that the atmosphere actually has a finite width, so that the Rossby wave may get into congestion. So it is not like the wave can travel freely. Like there is indeed a finite width that when the wave activity attains these values, like learn from this term, like the solar wave activity flux would attain a maximum. And that would be the traffic jam of Rossby wave in the jet stream. So in order to study this equation better, we define a saturation level, which is the flux term over like the maximum value it can attain, and then we can see if this saturation level is being approached, then we are closer to the onset of blocking. What affects the proximity to such saturation? So there are three factors. So the first will be the background flow in the jet speed embedded in C. The second one will be the stationary forcing represented in a model by A0. And the third one will be the transient eddy forcing, which directly affects the growth and the decay of the solar wave activity flux. So this, when we are studying how blocking frequency would be affected by warming climate or like jet shift or some other things, it is not easy to study it with GCM because like there will be cancellation effect or like coupled effect between different quantities. But if we are playing this in a very simple toy model, we can gain some insight while keeping them like keeping the comparison clean. Okay, so here I will talk about a recent study by my supervisor and some other students at U of Toronto, Woodhouse, and also U Chicago in the climate statistic workshop Rossby Palooza, organized by my department. So it is a like bi-yearly event, and yeah, it's a lot of fun. I was in the first organizing committee when this was founded, like in 2016. And so they are trying to play with this model and gain some insights of blocking statistics and like how it will change in a varying climate. So given the model is cheap to run, they can sweep the parameter space of like all the three controlling factors. So here I'm showing an example of their simulation. Here is a Hofmöller diagram. So it is time versus distance that it is traveling, and and here are the total wave activity, the solar wind, the flux, and also a blocking mass. So here they are defining the blocking as like an extreme where an extremum of the solar flux derivative. And I'm showing a simulation that they are using a slower jet, a weaker stationary wave versus a faster jet and a much stronger stationary wave. That the wave is like confined in the two bands here. So you can see like the change in the blocking mass, like the blocking statistics. Here there are more frequent blocking, but they are less persistent. While, yes.
I was just curious, does that relationship with the faster jet, stronger stationary wave explain why the Atlantic is more variable or unpredictable?
So Atlantic is like has the stationary.
Does the Pacific jet stronger and it's more predictable?
What do you mean by predictable?
You had a higher statistical relationship between wave activity and the zonal flow speed in the Pacific and the Atlantic. And I'm just wondering if it has to do with this relationship you're describing now, that a faster jet implies a stronger stationary.
Oh, I see. Because in the Atlantic, like the zonal wind, like due to the topography, the zonal wind is not so well correlated with the wave activity. As you mentioned. Yeah, that. So that might be the case. So over the Atlantic, yeah, there. In it, yeah, I'm thinking, yeah. So the stationary wave over the Atlantic, it would affect, but the stationary wave doesn't make it like more unpredictable. It's just like one of the controlling factors that would influence like the behavior of the blocks. But yeah, they are indeed different due to like the difference in the stationary wave pattern over the ocean. Yeah, indeed. Here I mostly want to show the effect of a stationary wave, but they indeed have used a faster jet as well. So here is mostly comparing like if there is a stronger stationary wave, how would blocking statistics behave? And so in fact, the jet speed and the stationary wave have an opposite effect influencing blocking. Here I'm showing 3 blocking statistics measure that they are using: the prevalence, the frequency, and the persistence. And for these 3 metrics, in the parameter space of the jet speed versus stationary wave amplitude, there is a clear transition boundary here that we can observe in all these 3 metrics. That the climate state can transit from a block-free state to a block-dominant state. So this is what we learned from this toy model. And one of the insights gained from it is that, like, at the current state that we are in, blocks are observed frequently, but like they don't last for too long in the real atmosphere, like in this scale. So maybe the present climate is around the transition state, so that when we are running different models, that we are actually falling on like different side of this transition boundary, so that the model can hardly agree on each other, having a low confidence in like projecting whether like the change in the future climate is positive or negative. Okay, so here's the end of my talk and a brief summary of it. So first of all, I'm introducing the finite amplitude local wave activity as a diagnostic to study atmospheric blocking, because it can capture the evolution of a large amplitude wave and also partitioning the physical processes leading to its progress in different terms. Secondly, the blocking can be modeled as a traffic jam in the Rossby wave. So we only focus on the zonal wave activity flux and can build a toy model that captures the behavior of block. The third thing is that the capacity of the jet stream or the proximity to saturation is affected by first the background flow, second the stationary wave forcing, and the transient wave forcing. And last of all, the parameter sweep with a simple 1D model give a clear transition boundary between block dominance and block free state. The proximity to this boundary might be a reason why model projection has low confidence in blocking statistics. So this is something that has to be further studied and verified. So we are providing some insights from like a simple 1D toy model. Okay, so after the introduction, I would like to introduce like a toolbox that I've been developing to wrap up the code to compute wave activity into a Python package so that you can compute things in 2 or 3 lines. Yeah, so there are some Jupyter Notebook examples that you can just stuff in your climate data, and then it will produce the computed results, and then you can plot it out, you can save it. And I'm still maintaining the package, and if there are some new functionalities to add, feel free to raise any suggestions or like issues on GitHub, and I will take care of it. Like even though like I have to work, I'm still I'm still maintaining this. So yeah, and okay, so that's the end of my presentation. Thank you for your attention.
So this wave activity flux, which what you're saying is it's kind of shut down during blocking because of this traffic jam, right? But the wave activity flux itself is creating the blocking, I would think, that it actually builds the ridge.
Yes.
So it's a natural break on the system as well. Once you build the ridge, you get this traffic jam, and then the wave activity flux would weaken at
And
that.
the wave activity flux would decay to 0 for a while, like when the block is formed.
But
Yeah.
what I'm getting at is there's one assumption built into that, and that's the wave activity flux is created by the movement of the waves. But in reality, in many cases, the wave activity flux is created by an independent entity like tropical weather systems.
Mm-hmm.
And in those cases, you may get continuous forcing of this ridge, which would maintain a traffic jam.
And so you are saying that locally at the block there are creation of wave activity by other systems? Or that?
Yeah, what I'm saying is in many cases, wave activity fluxes come out of the tropics. They come out of a different entity. They're
Yeah,
not.
so
They're
it's
independent.
Yeah, it's from like the meridional transport of wave activity. So here I'm so it is something that is worth looking at because I also see, like, for example, from my Bluefy, there are plenty of wave activity from the low latitude regions.
Mm-hmm. Yeah, that's right.
Yeah, and I guess so for the blocking cases that we have been looking at, it's mainly the congestion of the
Yeah.
wave activity upstream. So there, I guess that it would be worth doing some case study for those arising from like low meridional transport.
Exactly. Okay.
Okay.
Yes.
So, 2 questions. When you were showing that movie of the wave activity, it seemed that it was dominated by anticyclonic disturbances
Yeah.
on the maps. When you see very high wave activity, seemed dominated by that. I was just curious why that seemed to be the case. Maybe it was a misinterpretation on my part.
Yeah.
And then the second question, which is somewhat related to Greg's question, comes to the fact that, you're looking at this as sort of a modeling as a traffic jam. So if I'm a wave on this Rossby wave highway and I'm coming up to an intersection with another road, right? So this could be along the subtropical jet. You have a polar jet that's also dumping wave activity into a similar region. You have another source from, you were saying, a different latitude. Is there a way to account for that in your model to have a different, an on-ramp from a different road sort of merging with that?
I think you mean in the toy model?
In the toy model, right?
Yeah,
Is there a
in
way
the
to
toy
do
model.
that?
I think that would So since that is a 1D model, so we cannot get the meridional flux, but then it might be mimicked by a term like of forcing that represents the meridional transport.
Mhm.
And the first question
Yeah, that was about the wave activity seemed to be high when you
is
had anti-cyclone.
it's mainly I think it's mainly because the cyclonic system are of a smaller scale. So the wave activity is capturing the meandering of like a large omega block, but then the cycles are here, right? So, so that was over a 4-day period too, right? In your movie. The movie is not 4 days, like 1 month. Oh no. Yeah, so it's from it's from October 16th to November 15th. Yeah, so you're seeing like the cyclones. Let's see. Yeah, some cyclones are captured, but then like it is of rather small amplitude. Well, actually, when the anticyclone is there, there are also cyclones at the flank, right?
Mm.
So they are all captured together as zonal asymmetry. So there, the large wave activity block corresponds to the asymmetry that like consists of the 2 cyclones and 1 anticyclone.
Thank you.
Yes.
What about application to the Jovian atmospheres, where you don't probably have, at least not by eye, you don't have as much meridional transport between the bands, and yet you still have blocking in the Jovian atmospheres. Does the 1D model, have you tried that with a model of Jupiter's atmosphere?
I haven't looked into the Jupiter atmosphere, but the previous student in Nakamura's group, he was looking at Jovian dynamics using the finite amplitude formulas.
Oh, yeah,
So
yeah.
I think if you want to study localized things, then you can use local wave activity for that.
So with regards to using this as a blocking index, have you compared it to other currently existing blocking indices? So for example, there are some that use zonal wind,
Mhm.
and since you see this intercorrelation, I'm wondering if they give you similar results or if you find.
I attempted to do that before, but I eventually gave up after surveying like different, like maybe 2 or 3 blocking indices because they don't agree with each other. I do not know which one to use.
So if there was a paper, it was
Barnes?
by Elizabeth Barnes
Yeah,
who compared.
2014.
Who compared different blocking indices and found that you get similar results if you use the same thresholds and the same. So you can use it just in different fields, but you have to have the same thresholds, such as persistence or the longitudinal extent of the block. So I'm wondering if you have similar thresholds, then if you would get something like a similar blocking frequency or something different relative to what already exists.
Okay, so that's the paper by Barnes in 2012 on climate dynamics. I remember. I also read that. So she's saying that like if so you can use zonal wind, the true potential height, and also the potential temperature. If you go through the same pipeline, then you will get something similar. Then.
Because I imagine that you could take your index and then you can define thresholds, right? Because you showed a time series where you would get a peak during a blocking event, right? So you could say if this peak persists for a certain amount of time beyond a certain threshold, and it's 2-dimensional, so you could give it.
Yeah, but then even though I'm saying like it can be used as a blocking index, I would not go on the way to define some arbitrary threshold for the spatial extent or the temporal extent. Like I would just look at the wave activity itself because like the growth and the growth of it already implies the deceleration of the zonal wind. Like if I'm using wave activity as a blocking index, I would not do the same statistics as how others do with blocking index.
The only reason I mention it is just so that you can, I guess, compare, right? Because I feel like we spent a bunch of time at a blocking workshop being like, what is blocking in the first place? Because there are so many different definitions. If you were to use it as a blocking list, even if you don't define thresholds, or if you were just interested in the wave activity, you would probably be asked, how does it compare to what currently exists, even if that's not the way that you use it or decide to use it.
I mean, to compare it, I remember in Van's paper in 2014 on GRL, she actually showed that like for the same like geopotential high quantity, like the results can be different.
Mm-hmm.
So it's like if I'm also comparing it, so what shall I be compared with?
You could compare. I would say probably zonal wind, right? Because you saw an anti-correlation to zonal wind, and there are blocking-based indices, or zonal wind blocking indices. So it could be worth seeing how similar they are, or whether you're, I don't know.
Why don't I directly compare that with zonal wind then? Like at each
Well,
point.
for actually saying that a block exists versus something transient, like a transient high pressure system or something like that. So that's where the persistence would be a requirement.
Yeah, I really have tried that before, but then I cannot convince myself to like stick to a particular scheme. Like even for the zonal wind reversal, like if you slightly modify the definition, then the blocking statistic will vary. So, like it is not. I think it is not the way to go if I try to compare it with like some existing indices with some arbitrary threshold, like spatial and temporal definition of blocking. In fact, we have not been treating blocking as something very different. Like it is also Rossby waves, just that the Rossby waves are stuck together. So it's not like, or if defining blocking, then it will be like from what we know, then we'll look at the zonal wave activity flux to see if like there is a signature associated with this event. Like that would be the way that I think we shall go.
I wonder if you could go back to the formulation of the model, the original, the stochastic model.
This one?
So that's right, so can you? So in this case, the transient wave forcing is just a stochastic term that's added in, and the everything else on the right hand side there is symmetric, other than the wave flux there, which has the a squared term in there. So in that case, the F2. So in that case, the asymmetry in the model comes about through the dynamics of the low frequency itself compared to the dynamics of the Rossby waves.
Oh, you were saying like the.
No, I mean the a squared term there in the d by dx.
Oh.
I mean, yeah, the only reason there's any asymmetry in there, like everything else on the right hand side would be just Gaussian symmetry. Is that correct? Like transient wave forcing, linear damping, and numerical diffusion. If the transient wave forcing is stochastic, you would just have Gaussian statistics out of the system. So any sort of asymmetry comes from that term, which is what I'm saying is that term. The origin of that term is what I'm wondering about. Those terms can come about through either introducing those dynamics into the system, or oftentimes terms like that can come about through resolving the noise itself and looking at so we talked about state dependence earlier, the state dependence of the noise that introduces terms that can be question here, sorry. And the main point is, where's the asymmetry that comes, the asymmetry from this, I guess all comes about through the A term there, and I'm trying to figure out where that, how that relates to the wave forcing. That perhaps is a bad question here. I just.
I think I understand your question, like how you
That was the A squared is just coming from the nonlinear. I think it's the
Right.
slide previous, it's the more the nonlinear fluxes.
this
Yeah.
From
Yeah.
above.
yeah, from the above.
Yeah, it's the EP fluxes, right?
So it's, okay, so it's the nonlinear term that isn't accounted for in the EP fluxes. Okay.
I guess I'd like to ask a little more about this idea of capacity, which seems to be rolled up in that C term, right? And I think it's kind of the same question you had. That is that term. So UREF, you said, was that you got that from eventually from the equivalent latitude that you have for the PV, right? And you get a zonal wind out of that. Have you looked at how that term changes with time within the reanalysis? Do you see a change in the capacity over time?
So this UREF, you may refer to the paper Nakamura and Solomon 2001. They are computing it in different seasons, so it is a slowly varying state,
Right.
like with a very low frequency.
I'm just wondering whether there's any secular change in that within the reanalysis that might say that the capacity of this traffic flow has changed with time.
So it would change over the season, but then somehow over the season it changes, but it's likely along the line here.
But over
Like
decades?
Over decades. And then
No,
if you
just
look,
read that.
if you look at your stationary, so your other term is the stationary forcing, which to me is topography, which is not changing, and the monsoon, which might be changing. And I'm just wondering if you could take this insight from your toy model that says the capacity, right, is what might have a climate signal. Is the capacity to to have traveling Rossby waves changing with time so you get different blocks frequencies.
Interesting.
Yeah, this is something to look at. Like the stationary wave there are.
I mean, you kind of said you felt like maybe the reason there's uncertainty in climate models is you're laying right along this transition zone.
Yeah.
But it seems like you could look climatologically at how you reference vary
Yeah,
with
so
time.
like it pulls like up and down.
Yeah, right.
Or is
That's
it moving towards somewhere? And I'm not sure how you, and the stationary wave, I don't know how could you extract some information about that stationary wave forcing out of actual reanalysis?
Right.
Like, the strength, some measure of the monsoon circulation,
Yeah.
which I think also gets to why the Pacific is so more predictable, because it's driven by that
The Atlantic
monsoon.
Association. So we haven't looked into the like we actually computed the reference state and but then we don't have like the variability, interseasonal variability there. So this is also something that is worth checking, and also the trend of this reference states. And you can tell something.
Okay, any other questions for Claire? I want to remind everybody that Claire will be around. I think there's already some appointments scheduled for the afternoon tomorrow, so maybe only now the morning is available. She won't be leaving till about 3 tomorrow, so if you want to get on the schedule to talk to her, please do so if you haven't already. So, but thank you again, Claire, for